Okay. Um, Today we'd like to finish part of speech tagging uh, with some loose ends being tied, and I would also like to discuss conditional random field as it applies to part of speech tagging. Just before the deep learning era, the most important ML algorithm for sequence labeling, sequence processing was conditional random field. And before conditional random field, it was support vector machine. Okay, support vector machines were very successful in classifying textual elements. Okay, so sentiment analysis, document classification, they were very successful with the support vector machine. So when we say very successful, of course, much less compared to what deep learning is doing. But before deep learning, it was conditional random field. Okay. Can you settle down, please? Yes, settle down. So it was support vector machine and support vector sorry, conditional random field. And the second part of your assignment is using conditional random field for part of speech tagging. Okay, so this should give you a lot of insight into the problem of part of speech tagging and thinking of the correct technique for part of speech tagging. Now, it is necessary to appreciate those machine learning techniques like support vector machine, hidden Markov model, conditional random field because they prepare you for discussions on deep learning for NLP. Okay, why deep learning, after all, was needed, and why did it succeed so well? Okay, so that is required for understanding. That is facilitated by understanding support vector machine, conditional random field, HMM, maximum entropy Markov model, and so on. Okay, so those statistical algorithms are useful. So let's proceed. Can you stop talking? Please stop talking. Yeah, please stop talking. Now, so so we did this recap of last week's lecture. Now, let me describe some conditional random field in the context of your assignment. Okay, the statement of the assignment is to implement a part of speech tagger in Python using hidden Markov model. That is your first task. Input and output. The data set is Brown corpus, and the tag set that you have to use is universal. Output is the tag sequence corresponding to the input raw sentence. And you have to give accuracy statement, the performance figures. It should be 5-fold cross validation. Okay, that means you should divide the test corpus into 5 parts and divide the data given to you into 5 parts. 4 parts are used for training, and the remaining part will be used for testing. Now, for hidden Markov model, the training is a very simple operation. Training essentially finding out the transition probabilities from tag to tag, and also the lexical observation probabilities, that is probability of a word given a tag. Okay, this is the task that you have to do from the data. And in this case, training is not iterative, it is one shot. You directly compute the transition and lexical probability from the data itself. Okay, so for hidden Markov model, training is almost trivial. Okay, you just have to compute ratios. Confusion matrix is a very useful conceptual tool for classification tasks. Okay, so when a machine outputs a label and the golden label is also given a sentence, you know what the correct part of speech tag sequence should be, or given any position, what the part of speech tag should be. And suppose you've got a different tag there. So confusion matrix tells you which tag is confused how many times with other tags. Okay. So in this case, we know there are noun tags, verb tags, adjective tags, and so on. So you have to observe out of those approximately 40 tags, okay, which are placed on the rows, and columns are the observed tags. The rows are the ideal tags, columns are observed tags, and you have to find out which cell has how many count. Okay. Suppose you find that in the row corresponding to noun and the column corresponding to adjective, you have a large number. So this means that, let's say the number is 1347. So 1347 times the noun is confused with adjective, where the noun should have been output, you see the adjective. Okay, so noun adjective confusion is very common. That is mainly because in English, most of the nouns act as adjectives also. Most of the nouns act as verb also. Sorry. So noun verb confusion is very common. And so this confusion matrix observation is very important for you. You should produce the confusion matrix. And confusion matrix clearly links directly with accuracy. Then you also should compute part of speech tag accuracy. We expect that the determiner, DT, will have very high accuracy. Okay, the, for example, cannot be anything other than DT. But there also you do see confusion. Okay, DT sometimes is confused with noun, okay, or adjective. So this exercise you should do, and your demo should work. I would like to give you new sentences, and the system should produce correct part of speech. Then hidden Markov model needs to be implemented from scratch. As I have said, you have to compute the transition matrix, lexical probability matrix, everything from the data. Also implement by a recursive function call. Okay, you should implement the Viterbi algorithm also. So this is the assignment that is expected from you. Okay, at end of the month we'll look at this. Now, some of you have asked what to do about data sparsity, what to do about words which appear in the test corpus but not in the training corpus. So this is a case of data sparsity, and this is typically solved by what is called smoothing. So there are many different kinds of smoothing. Add-one smoothing is most popular. So in add-one smoothing, you just add one. Okay, if the count of some entity is 0. Okay, then there is Laplace smoothing. There is good Turing smoothing. So read up on smoothing. Smoothing has lots of material on the net. And the book by Christopher Manning on statistical natural language processing has an excellent treatment of smoothing. Okay. So smoothing in the deep learning era has become less of a problem. That is because if some word is not in the training corpora but appears in the test corpora, then because of the continuous space, because the words are represented in the continuous space, a nearby word is picked up whose cosine similarity is high with the other word. Okay, so cat and dog, for example, are likely to have very similar word embedding or word vector. We have not covered word vector yet. I'm just mentioning this term to you. Each word in a language can be represented by means of a vector. So the vector of dog and cat are likely to be similar. So if I do not see cat in the training data and it has appeared in the test data, because cat is similar to dog and because the part of speech of dog is noun, cat is also given the part of speech tag as noun. So in continuous space, these problems are less severe compared to discrete space. Now, this notion of continuous versus discrete space should be clear to you. Take the two words cat and cot, C-A-T and C-O-T. There is very high lexical similarity between them. Two alphabets are similar between cat and cot. But conceptually, as actual real life entities, they're so dissimilar. Okay, cat is an animal, cot is a furniture. Whereas between cat and dog, in the spelling of cat and dog, there is no similarity. There is no letter which is common between the spelling of cat and dog. but still they are much more similar than cat and cot. Cat is much more similar to dog than to cot. Okay, so these intuitions are established and exploited when we represent the words in a continuous space. How you represent words in a continuous space, that is another discussion, which we'll do little later. Now we live in the discrete space. There are language objects, namely words, sentences. These are discrete objects. Okay, but that is surely not a very useful stand, because we know that words are very close to meaning, close in meaning to one another, even though their spellings could be very different. Okay, and two sentences can be extremely different, but their meanings can be very similar. Right. So, and if you take the spectrum of universe of all languages and say that I do not care about the language barrier, then this problem is all the more severe. You have to work in the continuous space. So a bad workman quarrels with the tool. Okay, that means a person who is not efficient and skillful always finds excuses and finds faults with the tools. The corresponding Hindi sentence is Nach na jane angan tera. There is no similarity between these two, literally. If you take word by word translation, there is absolutely no similarity, but they mean the same thing, exactly the same thing. So it is all a matter of representation, and the natural language processing is deeply concerned with how language objects are represented. Okay, so that things which are actually meaning-wise close also are close in representation. If we take the dictionary entries, then that is not a good representation. Okay, because the index of dog, the position of dog and the position of cat, if you take positions as the representation, position in the dictionary, then they are not close. So we need another representation. Let me repeat this point. Okay, we need an appropriate representation for language objects, words, phrases, sentences, paragraphs, so that entities which are close in meaning are close in the representation also. Okay, that's an ask or requirement. So think about this, how to organize this. Now, you might come back and say, if when language slowly evolved, okay, maybe 40,000 years, 50,000 years back, why didn't human beings sit down, held a meeting, saying that, for concepts which are very similar to each other, we'll have similar words. 40,000 years back, they should have held a meeting. Okay, so dog is called dog. Maybe cat should be called dag. Similarity is preserved. They are very close. But the problem is that language doesn't evolve this way. Language has its own mind, so to say. Okay, language evolves organically. So wherever there has been any attempt at controlling that evolution of language, such attempts have always failed. So you created a language which is extremely controlled, grammatically beautiful, very extremely rule-obeying. Such languages are kept in the museum. And people go ahead and evolve the language as per the need, as per environment, as per their food habit, and so on. Okay, so language has a life of its own. So now let's proceed to how this assignment is done. This assignment is done by means of a search in the training space. So we have been using this example because it's a very simple example, but illustrates all the basic ideas involved in the HMM-based part of speech language. So we know that people can have two tags, dance can also have two tags. So then if you start from the hat symbol and finish at the dot symbol, then you have to navigate through a graph which is of this shape. On every word, Okay, you have a column of tags, and these tags are connected stage-wise. So this stage-wise connection produces a graph, and this graph has to be searched for the best possible path. That will be the most likely tag for the sentence. And this involves search. Okay, so from here, I have the choice of going to V or N. Then from V, I have the choice of going to another V or N. And from N also, I can go to V or N. So this is the way the graph develops. And we've seen that after a stage, if you are using bigram, then from the second word onwards, okay, from the second lexical word onwards, we can begin to prune paths. Okay, partial paths get pruned. Paths which end in the same state are processed, and the path which has the maximum probability amongst all paths ending in the same state. Ending in the same state, it's a key phrase there. Okay, only that path is retained, all other paths are pruned out. Okay? So this is how the Viterbi algorithm works. And from one node to another, we note the probability of the arc. The probability of the arc is augmented by the probability of the observation also. So we take the product of the transition probability and the observation probability, okay, from the source node, and that becomes our parameter for the final path. The final path must have the highest probability. That highest probability is the product of the product of two probabilities, a pair of probabilities, the lexical probability and the transition probability. And every such arc will be considered and the total path probability is computed. So this idea of searching for the best possible path based on the probability values is the basic idea. Okay. So it doesn't matter whether you're using hidden Markov model or conditional random field or maximum entropy model. Doesn't matter. Okay. This same idea remains. This same idea of getting the path. Let's see how it remains in the conditional random field also. So part of speech tag assignment statement, CRF part. Here you have the liberty of using available CRF tools. Okay, CRF was a very famous CRF, workbench, which is written using C and C++. But this has been upstaged by CRF suite, okay, which is very popular for NLP, and you can install the Python bindings using pip install Python CRF suite. This is the command. Okay, and another very popular platform is also PyTorch CRF. So do look at these tools: CRF++, CRF Suite, CRF Torch, PyTorch CRF, and there are others also. sklearn also has a CRF platform. The probability PT given W is modeled using discriminative modeling, which is CRF. So we covered discriminative modeling in the last class, which is supported by beam search. So you can use either of beam search or Viterbi to find out the best possible path. So let's look at what you have to do. So a bit of theory first. What is theory? CRF. It is a type of probabilistic graphical model. Now, what is a graphical model? Graphical model we have already seen in the form of hidden Markov model. A graphical model is a graph. Okay, a probabilistic graphical model is a graph which is a representation of a task and often comes with the requirement of finding the best possible path in the graph. So it's a type of probabilistic graphical model. We can make the definition of graphical model more precise, okay, at some point of time, but it's not really necessary. We know that a graph is a tuple of V and E. V is the set of vertices, E is the set of edges which connect, the node pairs. So it's a probabilistic graphical model. That means that the arcs in the graph and the paths in the graph, they have associated probabilities. Okay, and these are used for structured prediction. So structured prediction is used in natural language processing, used in bioinformatics, protein structure prediction, okay, gene sequencing, and so on. These are called structured prediction. So I'm using some phrases whose definitions you can look up, or if necessary, we can do it later. Particularly effective for tasks where the output variables are not independent, but rather have dependencies that must be modeled jointly. Okay, so you remember the assumption we made for part of speech tagging. We said that the tag at any position depends on previous K tags, and K typically is 2 or 3. For English, it has been found that previous 2 tags are sufficient to give high accuracy part of speech tagger. Okay. For Indian languages, no such study has been done yet. And I do not see these kind of observations coming for other languages. So deciding on the Markov window is a design parameter or a hyperparameter that needs to be fixed before. So CRF basics are as follows. CRFs are undirected graphical models. They model the relationship between variables without assuming a specific direction or influence. The structure of the graph represents the dependencies among the variables. Now, structure of the graph. You see, if suppose you are concerned with adjective and noun relations only, then given the word sequence, you will connect only adjectives and nouns. Okay, and leave out other connections in the graph. So this may be useful for some purpose. The point is that the graph actually encodes the dependencies. Now we have to model probability of y given x, where y is the set of levels and x is the set of observed features. Okay, so note the change in the wording. X is the set of sequence of words. But now X has become a set of features. So what is the input is the sequence of words, but you have the set of observed features. So this discussion we had in the last class, where we said that at every position we would like to obtain the part of speech tag, and that part of speech tag is a function of features with respect to that position. Now, features with respect to that position gives you a lot of freedom. Feature at a position gives you a lot of freedom. What freedom? I can choose the word itself as a feature of that position, which is a nice way of looking at the problem. The part of speech tag of the previous 2 words with respect to this particular position are additional features. The word that you have at that position, what suffixes does it have? Those are again features. Okay. What is the word coming after this word? You cannot take the part of speech tag of the next word as a feature because that part of speech tag has not yet been found. But the subsequent words, other properties you can find. Is the next word a noun? No. Sorry, noun would be part of speech tag. Does the next word have a shun suffix? T-I-O-N. Okay, so those kind of questions you can ask, and you can design a very elaborate feature set. Of course, the longer the feature set, the more is the computational complexity, and more can be the misleading information also. So I'll specify soon what kind of features you should use for your CRF-based part of speech tagger. So we have to model Py given X, where Y is the set of levels and X is the set of observed features. So formal definition, given X, which is the sequence of observed variables, that is words in a sentence, and the words are X1, X2 up to Xt. The Y is the sequence of output variables, that is levels corresponding to each word, Y1, Y2 up to YT. The governing equation for this particular probability Y given X, is given by this template. We have 1 by Zx multiplied by e to the power sigma c psi c yc comma xc. This is the formula. Okay. So what does this mean? Psi c yc comma xc is called the potential function. Okay. And these potential functions are over the clicks in the graph. Click C in the graph. Okay, what does that mean? Subsets of variables that are fully connected. So what it means is that, okay, this takes us into some graph theory. Those of you who have not been, let's say, exposed to this, it only means a part of a graph, okay, which is fully connected. Okay, that means there is a pairwise connection for every pair of node in that subgraph. Okay, in that part of the graph. So what it is saying is the following. You should note down all the theory actions. What is written in the. Okay, suppose we have a graph of this kind, and we have this kind of dependencies. Okay, B depends on A. Let's say A also depends on B, and so on. So these arcs represent a pair of nodes which have dependency between them. Okay. What is this dependency? We'll not worry about it now. Let's keep this abstract. So probability of A, B, C. This joint probability can be written as probability of A, the probability of B given A. This is chain rule of probability. Probability of C given B comma A. Probability of C given probability D. Okay. So now we see that B depends on A and D. Okay, B depends on A and D and nothing else. So I leave it as such. No problem. Yeah. What about C? C depends only on D. So C depends only on D. Then I do not. I say that C is independent of B and A. Okay, so this will be just probability of C. Probability of D. D depends on A, B, C, everything. Okay, A, B, C, everything. So I have to leave all this here. Okay. So if you have a fully connected graph, that this becomes all the more apparent. Yeah. Yeah.
So the sequence wouldn't get like there would be any.
So you will have a special kind of graphical model here. Okay, it's a chain graphical model. You will find a path. You just okay. So I want to model. I want to express P A B C D, which is the graph, and the click C is a part of the graph which is fully connected. Okay, and then we say that the probability of a node, the probability of let's say X, depends on a subgraph of G, which is fully connected. So why fully connected? How to take that particular part of the graph, which will determine the probability. Okay, a particular conditional probability. That let us explore slowly. So anyway, so probability of y given x, which is what we are concerned with, is expressed in terms of a normalizing factor zx, which is a function of the input, and multiplied by e to the power a potential function, okay, which is a function of both yc and xc, where y and c, x are levels of a connected subgraph of the graph. Okay, let's proceed. But how does the potential function look? Psi c, yc, comma xc. So this looks like the following. It is e to the power sigma lambda k fk yc xc. Okay? Things are very abstract so far, but when you bring it to part of speech tagging, they will take a concrete shape. So we take that particular subgraph and see what features exist, okay, for that subgraph, where we have the labels and we have the observations. Okay, so for every word, we have a label in the training corpus, and that label and the word are available to us in the form of a graph. And when you take a connected subgraph, we observe all the features. Now, these features are given weights, lambda k. Okay? There are, let's say, capital K features. So small k goes from 1 to capital K. So there are these features which are collected, and each feature is given an importance, a weight value lambda. Okay. So fk, yc, xc is the feature functions, lambda k is the weights of the features. So these things are very abstract so far. So you will get an extension of 1 week, okay, 1 week to 10 days for implementing this CRF-based part of speech tagger. We'll have to spend a little more time on this, discussing the theory. So probability of y given x has this form: 1 by normalizing factor plus e to the power a summation of potential functions. So this is equivalent to, now we are expanding the potential functions. So for part of speech tagging, it has a particular shape. For part of speech tagging, we have psi I, y I minus 1, y, and x. Okay, and x is the input. yi is the level at position number I. I minus 1 is the level at position number I minus 1. So this is considering levels of adjacent positions. Okay. So levels of adjacent positions, the input string, and phi I is the potential function at every position. Okay, so look at this example once again. We have hat, people, dance, and then dot. There are 4 tokens here. So now I would like to label this sentence, and I'm interested in finding the probability of the label sequence given the input sequence. So in hidden Markov model, I have these transition probabilities, probability of V given hat, probability of N given hat, and so on. For conditional random field, I have this graph. Okay, I have this graph, and this graph now does not have these outgoing edges going to the words. That is not there anymore. Okay, you have the labels as the nodes of the graph, and at every position we have a feature function. Okay, so that feature function decides the probability values of transition going from one level to another. Finally, we have to find out the best possible path in this graph. Only thing is that the transition probabilities are determined by the equations there. Okay, and equations there. So this is the governing equation by which we get this level to level transition probabilities. Okay. I know it is not fully clear to you. Okay, the most important thing here is that we have a different model for transition probabilities. Okay. The transition probabilities ultimately determine the best possible path. Yeah, just 1 minute. Huh? Best possible path. And the graph here is the graph which is coming from the hat symbol ending in the dot symbol, and in between you have various levels. Yeah. Different way. That's what it is. And these transition probabilities also take into account the words in the positions as features. Okay, you can take the words themselves or properties of the words, like the parts of the words, for example. So in your assignment, for example, what you will have to do is that you will have to take the words and break them into their suffixes and roots. So if you have boys, for example, you will have boy and s. If you have quickly, quick, and lee. So this is the way you will have to break the word into its parts. Now that will require what is called a suffix splitter. Okay, so look for suffix splitter on the net. We are likely to get a good suffix splitter, or you will have to use what is called byte pair encoding, BPE. These are statistical splitter, BPE. So BPE is a statistical splitter. So quickly will be split into quick and lee most of the time. And if you have a very large amount of corpus, high quality corpus, then byte pair encoding will break the word into correct parts, linguistically acceptable parts. Okay, so with sufficient amount of corpus, a statistical splitter can simulate a linguistic splitter. So I'll specify all the steps carefully in your assignment. Okay, and that should help you. Yeah. Yeah, tag given feature. So you see probability of y given x. Okay, this will have to be looked upon as a sequence probability, and also will have to be looked upon as a joint probability given the n. And the joint probability will have to be broken up into small parts depending on the dependency. And those small parts will be modeled by an exponential distribution, which is a function of features. Roughly, this is the idea. Lots of details have to be worked out for this. And the tool that you will use will help you in doing all this. But the key point is this: the transition probabilities are modeled in a different way. Let me write it down. Yeah. I couldn't hear you. Why shy is taken? So psi is taken, psi is called the potential function, right? Now, psi is the model of the probability of a level given a subgraph which influences that node. That is the idea. Okay. For part of speech tagging, that graph is a much simpler graph. And ultimately you get a chain. Okay, not a subgraph, but a chain. So that chain's probability is obtained from the transition probability of adjacent nodes. Okay, so it is a transition probability which is a function of the features. And all these attempt at using CRF, MEMM, they came from the need to incorporate features in part of speech tagging. Okay. I think we will develop this little further. You please start reading on CRF and also making use of the CRF tools. PyTorch CRF, then CRF suite. All.
Okay, so auto-speech tagging has nice algorithmic aspects, and there are many nice things about the modeling. So hidden Markov model-based solution of the problem will show you generative modeling for auto-speech tagging, and conditional random field-based solution will show you discriminative modeling. Okay, let me just say once for all that in generative modeling, the words, their transitions and observations play a role. You do not look inside the words and look at an internal structure. In conditional random field-based modeling or discriminative modeling, you will take different features, and those features are based on the parts of the words and the properties of the words. Okay, so we have seen discriminative part of speech tagging through MEMM and to the reason for agglutinative and pre-word order languages using discriminative modeling. And the beam search, I suppose, is quite clear to you, which is again based on the probability values. And this was the part of speech tags, which is almost universally used. Other languages also have made use of the English part of speech tag set from University of Pennsylvania and built their own tag set. Okay, they had to modify it for their own language phenomena. So now, when you report accuracies, what will you report? Okay. So we understand that at every position, we have the words and which are observations, and we have the part of speech tag at that position. So at every position, we will have the gold standard and the observed output from the machine. So the measures which will be used are precision and recall. In the most general case, the precision will be discussed by means of a Venn diagram like situation, where we have the first set S1, that is the set of levels obtained from the machine, and S2 is the actual set of levels. Now, S1 intersection S2, okay, which is the which has a number of stars in it. So this is the set of true positives. True positives means the outputs which agree with the true levels. The output of the machine which agree with the true levels. Okay, and S1 minus S1 intersection S2. That means this region, okay, this red dot region. This is S1 minus S1 intersection S2. This is the set of false positives. Why false positives? They are looked upon as true levels by the machine, but actually they are outside S2, which means they're actually not true levels. Okay, so this is false positive. And similarly, S2 minus S1 intersection S2 is the false negative region. Okay, we have missed those levels. The pink region has been missed by the machine. So this is a false negative. That means this is a case of erroneous omission. So the pink region is a region of erroneous omission. The gray region is the region of erroneous commission. Okay, so error of commission and error of omission. And S1 intersection, S1 union S2, the whole set, complement of this is the set of true negatives. Okay, so this is a useful picture. And precision is S1 intersection S2, that is the true positive region, divided by S1. Okay, the machine's output, that being the denominator, and the numerator is the set of true positives. And recall is the set of true positives divided by S2, the set which should have been totally obtained. Only a part of this is obtained. So recall is S1 intersection S2 by S2. Now we would like to combine precision and recall. Why so? Because precision and recall has this kind of falling curve. You cannot gain both unless you inject something extra. Many times it is extra knowledge into the classifier. So if you increase recall, precision falls, and vice versa. So you have to strike a balance between the two. Though of course you want to increase both precision and recall, but they have this falling behavior. So we come up with this measure called F score, F beta score. So F beta score is written by this formula 1 plus beta square P into R divided by beta square P plus R. Now this can be written again as 1 by beta square by 1 plus beta square R plus 1 by 1 plus beta square P. As beta tends to 0, F beta tends to P. Okay, so low value of beta will mean the precision is given more importance. And if beta tends to infinity, then F beta tends to recall. So as beta increases, recall is given more importance. Now, the usual cases are beta equal to 1, okay, where precision and recall both are given equal weightage. Then F1 becomes equal to the harmonic mean of precision and recall. It becomes 2 into PR by P plus R. Now the question is why harmonic mean and why not arithmetic mean or geometric mean? So arithmetic mean, you see, prefers the larger of the entities. Okay, arithmetic mean, you see, shift towards the larger of the entities. Harmonic mean shift towards the lesser of the entities. Okay, so now since you want to improve both precision and recall, then F1 measure is a good measure because you are paying attention to lesser of the two entities. Okay, lesser of the two entities. So if you want to have an increased performance for the system, then increasing F score will mean that the lesser of the two entities are improving. Okay, so how does the beta score, how does F score improve? You take more data, you take more powerful machine, okay, thereby you increase the F score. And then you can be sure that the lesser of the two entities are increasing. So this point should be clear to you. This depends on the property of arithmetic and harmonic mean. Arithmetic mean prefers the larger entity. Harmonic mean prefers the lower entity. Okay, harmonic mean is governed by the lesser of the two entities. Arithmetic mean is governed by the larger of the two entities. Okay, so this property of mean you know. Then, so what you will report is precision, recall, and F score. Okay, for your part of speech diagram. Now, in your case, if you are producing a part of speech at every position, then think about this. Then both precision and recall will be equal. Okay, if you're producing a level for every position, you're not missing any position. And gold standard data also has a part of speech tag for every position. None of the positions are missed. If you are wondering why this point is coming up, you can have a case of noisy annotation. So human beings have been employed to create labels for the data, to keep part-of-speech tag levels of the data. Maybe towards the end of the day, the annotator is very tired, sleepy, and misses a few words. Okay, so if that is the case, then in the gold standard data, you will not have all the labels. And the machine maybe produces only very high probability levels, or levels which have a probability value greater than some threshold. So this is a big problem in deep learning systems, okay, where softmax function computes the probability and outputs a language element. So if the probability value is too low, nothing will be produced. Of course, in hidden Markov model-based system, you will not have that problem. Conditional random field might get into this problem, and the data may have the problem of missing level. So in case of missing levels, precision and recall can have different values. In case of a sequence where every level, at every position you get a level, their precision and recall have to be equal. Think about this point. Okay. The size of S1 and S2 will be same for sequence leveling. If at every position you have a level, then the denominator will be same for both, and numerator is same anyway. Okay. Now, let us have some qualitative discussions. Why part-of-speech tagging is a disambiguation task? And if part-of-speech tags are not disambiguated, what will be the problem? So in the early days of natural language processing, we had rule-based part-of-speech tagging. So rule-based natural language processing is also called model-driven NLP, where a human expert with knowledge of language and the task will create enormous number of rules to solve the task. So when some data became available, we had statistical machine learning based part-of-speech tagging, and hidden Markov models were extremely successful. They defeated all the rule-based systems existing at that point of time, and that ushered in the era of statistical NLP. Statistical NLP started with hidden Markov model-based part-of-speech tagging. Support vector machines were very successful in document classification. Then came neural-based part-of-speech tagging or sequence leveling, which is today's transformer-based GPT-based system and so on. Now, why is part-of-speech tagging? Why correct part-of-speech tagging is necessary? Here are a few examples. So if you look at this phrase, command center to track best buses. So this was a newspaper headline in Times of India, Mumbai edition. This is 30th January 2021. So command center to track best buses. So you have a control center which tracks the buses flying in the streets of Bombay. Okay, it tracks those buses. Now command can be both verb and noun. If the part-of-speech tag of command is looked upon as verb, then it has a very strange meaning. It is asking us to give an order to Delhi to track the Mumbai buses, which is a very strange meaning. It is particularly odd. The next one also is an example of that kind. Elderly with young, that is where the pause should be. Elderly with young face increased COVID-19 risk. This is understandable. Okay, old people who have young children or young members in the household face increased COVID risk. But change the part-of-speech of face to noun. Okay, so people who are old and they have a young face, okay, they have increased COVID-19 risk. This is again a strange meaning. Okay, so correct part-of-speech tagging is necessary. Otherwise, the meaning can be completely distorted. since part of speech tagging feeds into subsequent stages of subsequent NLP tasks, it is very crucial for parsing, which are going to begin next week. Okay, so look at this sentence. Maharashtra reports increased COVID-19 cases. Okay, the state of Maharashtra is informing there are increased COVID-19 cases. So increased here is adjective. Now change the part of speech of increase to verb. The reports in Maharashtra, they increased COVID-19 cases. Okay, so can newspaper reports increase COVID-19 cases? Maybe in some subtle way. I don't know. So the dependency parsing shows that reports is the main verb. Okay, and if increase becomes the main verb, then the sentence has a very strange meaning. So reports is the main verb, Maharashtra is the subject. So that's why you have this N sub as the level. And the increased COVID-19 cases has its own dependencies. So the object of report is cases. What kind of cases? COVID-19 cases. So COVID-19 is adjective modifier, A mod. And increase is another adjective modifier, so double A mod. There are two A mod. So these labels we'll do as we move forward. So increase should not be the main verb here. Then the meaning is completely distorted. Interestingly, where is the distortion of meaning caught? At which layer? It is caught at the semantics layer or pragmatics layer. It is impossible that newspaper reports will increase the COVID-19 cases. So you have to invoke word knowledge, and that takes us into pragmatics. And in the Buffalo sentence, we have seen. Now, I'll present to you, actual difficulties faced in creating rule-based part-of-speech tagger, and why part-of-speech tagging definitely moved to data-driven solution. Okay, so look at this sentence. He gifted me these that present, and they present innovative ideas. He was present in the class. So the word present appears in three parts of speech in the three sentences. He gifted me a present. Present is noun. They present innovative ideas. Present is verb. He was present in the class. This present is adjective. So now I'm sitting down and writing a base part of speech tagger. That means I'm writing rules for disambiguation. Amongst all the part of speech tags, which one is applicable? So if I create this rule, if present is preceded by a determiner, the A or demonstratives, this, that, then part of speech tag will be a noun. Suppose we have this rule. And this rule looks very intuitive, seems to make sense. If a word is preceded by a determiner or a demonstrative, it has to be a noun. Now, is this rule foolproof? So let us be technical here. Will this rule have false positives? That means it will tag words as noun when the word should not have been a noun. Or will it have false negative? That means it will omit nouns to be labeled as nouns. That will be a case of false positive. So what do you think? Is this rule robust, foolproof? Can you find exception to this? Yeah. So the present generation is very tech savvy. The present generation is very tech savvy. The present is preceded by the, but it is an adjective. Or as you said, these present interesting cases. these present interesting cases. These are verb. So we have been able to immediately find these are false positive or false negative. The present generation is very tech savvy. By this rule, the present will be tagged as noun. False positive. I have committed wrongly. And these present interesting cases, false positive or false negative? Again, false positive. Wrongly tagged as noun. Can you find a false negative for this rule? Presents were distributed. Yeah. Presents were distributed doesn't have a the, but it's a noun. Yeah. Okay. So, so this that doesn't eliminate false positives and false negatives. Still, you might come back and say that I still don't see the reason why I should go statistical. Maybe the rules will have to be expanded. There, you'll have to make it more and more refined. You'll introduce more rule. Then I'll not need data. From my brain, I'll create rules for doing power speech tagging. Okay, so let's see. So I do both look back and look ahead. If present is preceded by determiner or demonstrative or followed by a verb, then part of speech tag will be a noun. Okay, so present will tell the future. Here it is a noun. Present foretells the future. Also is a noun. So the rule is an or rule. Okay, so if it is preceded by a determiner, it will be a noun, or if it is followed by a verb, then the part of speech tag will be noun. Now the point is that there are two rules here. Two rules are operating. Okay, so which rule should I choose is another difficult. Which rule should get precedent? Okay, so when we have rule-based systems, it is often a very difficult question deciding on the priority of the rule. Okay? Those of us who have gone through an age called expert systems age, knowledge-based systems age. So people used to create expert systems, a machine that will, an AI agent which will simulate a doctor, completely rule-based. So thousands of rules. Now a big point is which rules should get precedence when the situation demands or situation satisfy application of many rules. The rules are always challenged by new data. We need therefore a robust system. And that actually gave rise to machine learning based part of speech tagging. When it was realized that it is impossible to create a 100% robust part of speech tagger. There will always be cases which will be outside the scope of all the rules. And then deciding on rule priority is another challenge. So what did we do? We decided that the NLP community decided that we will live with imperfection. Okay, live with imperfection. We will not be correct 100% of the times, but we should be able to give guarantee how many times we can be correct. What percent of time we will be correct, and with what probability. So that is how probability came into the solution of tasks. And you know that probability, any probabilistic approach is impossible without data. So that is the historical development which introduced data into natural language processing. Otherwise, in the beginning of NLP, people thought that NLP does not require any machine learning, any data. Linguistics is sufficient. Experts with understanding of language and task will sit down, give rules, and done. NLP system will be created. But imperfections appeared, lots of new cases could not be handled. Then it was understood that probability is inevitable. Okay. Now, let me finish the lecture by just pointing to you one important concept. Probability of observation sequence. So probability of a sequence of words, for example, this we understand is the language model. So probability of observation sequence can be found in the following way. Probability of the observation sequence has to be found out by introducing the state as a random variable. And introduction of the state as random variable is possible only by marginalization. So probability of observation sequence will be equal to summation over all possible states of the joint probability of PO, S. Now, PO, S can be divided as PS into PO given S. Now, fortunately, we have both these parameters computable. PS, I can make bigram assumption and turn it into a product of transition probabilities. And P of O given S, I can make again Markov independence assumption and turn it into product of observation probability. So we have product of transition and observation probabilities, summation over all possible states. Now, summation over all possible states will be an exponential computation if we do it foolishly. But by making use of Viterbi-like pruning idea, we can have a very efficient algorithm which is linear in the length of the observation. This algorithm is called forward-backward algorithm. So forward algorithm. Forward algorithm looks like this, a recursive algorithm, and backward algorithm also looks like this. So for completeness sake, we'll do forward algorithm, backward algorithm, and then Baum-Welch algorithm for hidden Markov model. We will do them as tying all the loose ends, but we'll start parsing